Okay, looking at the first three big ideas on this page, it looks like continuity is going to play a vital part in our video today. Continuity on an interval. It's only continuous on an interval if every point in the interval is continuous. We have open intervals. Okay, the function has to be continuous at every point in the interval. And now, this is where we're going to talk about endpoints. We left that alone with our last video. We weren't really sure what to do. But for a closed interval, if the one-sided limit leading up to that endpoint is the same as the function value, we can say it's continuous on that endpoint. Okay, and an example will help cement that idea. So here is our favorite graph, graphus interruptus. We will be looking at different intervals. So we have from -5 to -2, not including those values. So we're looking right here. So at every point there, it is continuous because every point within that interval is continuous. Now this one, we have -5 including -2. Now we have a problem. This is going to mean no. Let me write this smaller. Because the limit as x approaches -2 from the left is not equal to the function value at -2. Okay, so the limit is infinity, but the function value is actually 2. So that doesn't give us an answer here. All right, back to this. Now let's look at -5. Is the function value equal to the limit? That's another yes. The limit as x approaches -5 from the right is 1. The f of -5 is also 1. So the limit, the one-sided limit equals the function value, so it is continuous at that value. This one is no for the same reason that we had in part B. The limit as x approaches -2 from the left is not equal to the function value at -2. All right, let's look at a couple of different places. 0 to 4. 0 all the way to 4. No, it's not continuous at all because it's discontinuous. We'll say no, it's discontinuous at x equals 2. All right, now we're talking 6 to 8. Let me clear that out. So let's start at 6 and go to 8. This is no for because of this part. The limit as x approaches 6 from the right would be 3. F of 6 would be 2. Those values aren't the same. All right, and then lastly, let's look from 2 to 4, here to here. This one would be yes because we're not including that 2. If we were including that 2, that would be a problem. But all of these are continuous in between 2 and 4. All right, let's clear this stuff off the graph now. Find the largest value of b such that the function is continuous on 5, not including 5, all the way to b, but not in this. All right, so we can go from 5 to, all right, it looks like it stops continuous right here at 6. Okay, or at 7, but it's not including 7, so we can't have that. Could we have, so it stops being continuous at 7. So if, let's let b equals 6, it would be continuous on this interval from 5 to 6, but not in 5 to 7. Okay, so b equals 6 would be the largest we can have. Now we have give the largest interval, so that from a to 10, not including 10. All right, well, 10 appears to be right here. So it looks like we could start at, so what's that, 6, 7, 8, okay? So it looks like we could have a equals 8 because it's, actually this was 8 here. It's discontinuous at 8, but we're not including it. There's a parenthesis, not a bracket. All right, and then the last thing, find the smallest value k such that the function is continuous on that. All right, so we have let's make it an oh, I lost my train of thought there. All right, let's try that again. So it looks like the smallest value that it could be continuous on an open interval would be right here. All right, so if that's 15, we have 14, 13, 12. It looks like it would be at k equals 11. We can include it because it's an open value. All right, let's keep going. Let's talk about continuous over their domain. That's another way of wording something. So, like arctangent, they're continuous for all real numbers, exponential functions, sine and cosine polynomials. All right, but rational functions such as square root of x, that's not rational. It's irrational, isn't it? Rational, like 1 over x, okay, x over 3, 1 over x plus 3. They're continuous for their domain. For example, this would not count -3. We know it's discontinuous there. So we're going to be talking about those, and then the continuity of combinations of functions. You can review these properties. We're going to use them. All right. Example 8 here, describe where the following functions are continuous. Now, x squared is continuous for all values of the real numbers. Sine, if you can put any number into it, sine of x is continuous for all real numbers. Therefore, h of x is continuous for all real numbers. All right, let's talk about this part now. Cosine of x plus 1, we start with the inside. That's always continuous because it's a polynomial function. And the range, okay, the numbers that are going to be coming out of this part are the lowest that cosine can be is -1. So that's going to be 0 for the lowest value of cosine of x plus 1. The highest value cosine of x could be is 1. So the highest value that expression could be is 2. The range would be 0 to 2. Now, let me change colors here. ln of x is continuous for all x values greater than 0. Okay, so whatever we're putting inside of there cannot equal 0, but we have a problem because we just wrote that the range could be 0. So we have to figure out that h of x is discontinuous. All right, when cosine of x plus 1 equals 0, or we could say cosine of x equals -1, or we know that to be pi, or any multiple of that, where n's an integer. Okay, we know that. It could be -1, +1, whatever. So the h of x is continuous for all real numbers except for this, or we could say it's discontinuous whenever x equals either of those. I just want to briefly introduce the intermediate value theorem, the IVT. All right. It basically is saying if we start at this y value and we end up at this y value, if the function's continuous, it has to cross every single y value in between those two. Okay, so say it starts at 4 and ends at 10 as y values. Well, it has to hit 4.5, 5, 6, 7, 8, 9, 9.1, 9.17. Okay, it has to hit every single y value in between those. That's what the intermediate value says. It seems as if it's common sense, but it's going to help us by having a specific theorem for this. All right. So the if part must be true before we can apply the then. So if a function is continuous on a closed interval, we have to check that when we're going to use this. All right. So determine if the IVT applies to the following function. Well, we need to know if it's continuous. So let's factor this to figure out where it's not continuous. X minus 2x plus 4 over x minus 2, x plus 3. So there's a hole at x equals 2. There's a vertical asymptote at x equals negative 3. So does the IVT apply? Is function continuous from -1 to 1 on a closed interval? And it doesn't include either of those values we listed, so yes, f of x is continuous on the closed interval -1 to 1. So the IVT would apply here. 0 to 3. I'm going to say no, f of x is not continuous at x equals 2 because there's a hole there. All right, for your whisk, I'd like you to explain letter C. Does the IVT apply? And explain why or why not. All right, and then for the last one, I'll answer this. Does the IVT apply? This is a no because it is not a closed interval. It has to be a closed interval. Because we have this parenthesis here, makes it so that we can't use the IVT. All right, so we will continue this with our next video.